Now, previous lecture we talked about different representations of an LTI system. We know that one such representation is the so-called state space representation. So we have x equals ax plus bu and y equals cx plus du. Okay, so this is state space representation. Another representation is the transfer function representation, where we have in general a matrix in Laplace domain called denoted usually by g of s, and it's called the transfer function. And what it does is that in Laplace domain it transforms the input to the output through this product, okay? Provided that the initial condition of the system is 0. Now, since they represent the same system, we should be able to go from one to the other. And in the previous lecture, in our last lecture, we went from the state space representation to transfer function representation, and we obtained that g of s, okay, in terms of the parameters a, b, c, d, should equal c times si minus a inverse b plus d. Now, in this lecture, we're going to talk about the reverse direction, namely, given a transfer function representation of an LTI system, how can we find four matrices A, B, C, D, so that we have, for the same system, a state space representation. Okay? So, in particular, we will be dealing with the following question. Given transfer function g of s, how to obtain the matrices A, B, C, D such that when put into this expression, the right-hand side becomes equal to the given transfer function g of s. Now, it turns out that this direction is significantly, maybe not significantly, but a little bit harder than this direction. And that difficulty has to do with, at least in part, by the fact that for a given transfer function, this quadruple satisfying this equation is not unique. Whereas for a given state space representation, the corresponding transfer function is always unique, so that we have this formula. Okay. Now, this is the nature of the answer. The quadruple A, B, C, D, which yields this equation, is not unique. Okay, so that means there are many different possibilities for those four matrices such that all satisfy this equation. Now, in this lecture, we will talk about just one method that would, for a given transfer function, that would give the quadruple ABCD. It's called the controllable canonical representation. And instead of giving the general rules, we're going to go over that method through an example, and hopefully the steps in that example are clear enough so that if needed, they can be generalized for other situations. So let's consider the following case. Suppose we're given the transfer function of a system with two inputs and two outputs. Okay, therefore, we're talking about a case where u is a vector in R2 and y2 is a vector in R2. In that case, this matrix will be a 2 by 2 matrix, okay, of a 2 input, 2 output LTI system. Be given as follows: G of S equals, now each entry of G of S, or a transfer function matrix in general, is a proper rational function. And in this case, in our example, this is what we're given: 4s minus 10, 2s plus 1, 3 over s plus 2, 1 over 2s plus 1, s plus 2, and here we have s plus 1, s plus 2 squared. Okay. Now for this G of S, we are asked to find a quadruple. Okay. Those 4 matrices that satisfy CSI minus A inverse B plus D equals the given transfer function matrix G of S, which is here. Okay. Now here is a solution. It's a solution because solution is not unique. Here is one systematic way that can be followed to obtain the quadruple ABCD for a given transfer function. And this method, sometimes called the method for obtaining the controllable canonical form. Canonical representation. Okay, step 1. We will try to obtain or construct a solution through some simple steps. Step 1 is writing G of S as a constant matrix, possibly 0, plus another matrix such that its entries are strictly proper rational functions. Okay, so if G itself is strictly proper, then step 1 can be just overlooked. Okay, you can just go to step 2. But in our case, this is strictly proper, this is strictly proper, this is strictly proper. But here, the degree of the numerator and degree of the denominator, they are equal to one another. Therefore, this entry is not strictly proper. Therefore, GS itself is not strictly proper. Hence, step 1 is necessary. Okay, for this example. So what we do is you write G of S in the following form. Note that the highest degree term is 4s. Here the highest degree term is 2s. So if you divide the coefficients 4 over 2, it's 2. Therefore this fraction can be written as 2 plus a strictly proper rational function. Okay? If you do that, what we have is have 2 plus minus 12 over 2s plus 1. Okay? So what you do is you write this as some constant plus a strictly proper transfer function. The others are already strictly proper, therefore we don't need such separation. These entries are 0 and the remaining entries are the same. S plus 2, 1, 2s plus 1, s plus 2, and this is s plus 1 over s plus 2 squared. Okay. Now, this, let's call it G bar of S, which is now a strictly proper matrix. And this matrix will turn out to be our D matrix. in the very end, the matrix of the quadruple here. Okay. Now, this is step 1. Again, it can be, we don't need this step if g of s is already strictly proper. Step 2, okay. Find a common polynomial by looking at the individual denominator polynomials. Okay. Find a monic common denominator polynomial. Okay, and we're going to call it g of s. Okay, so monic simply means that the highest order term, the coefficient of highest order term is 1, and one such polynomial is the following: g of s equals s plus 1/2. That's representing this 2s plus 1 term. Okay, so it has another 2s plus 1 here. We have s plus 2, we have s plus 2, we have s plus 2 also. So we have two terms. It appears one is 2s plus 1 or s plus 1/2, the other is s plus 2. But s plus 2 term appears twice here in the same entry. Therefore, it should also appear at least twice in our common polynomial. Okay, so we have to therefore have s plus 2 squared. Note that with this choice, every individual denominator divides this polynomial g of s. And in open form, it reads as follows: s cubed plus 4.5 s squared plus 6s plus 2. Okay, step 2 is over. Now let's move on to step 3. Now, step 3 is as follows. Now, we express our strictly proper part of transfer function, which we're calling g bar of s. Okay, write g bar of s as g bar of s equals g bar of s equals something, okay, that's being divided by our common polynomial g of s. Okay, and this something is the following: minus 6s plus 2 square 3s plus 1/2 times s plus 2 1/2 s plus 2, and here we have s plus 1 times s times 1/2. Okay, it's just a simple re-expression of g bar of s. No, that this divided by d of s gives you the first entry. This divided by d of s gives you this first row, second column entry, and so on. Okay. And that we will now write it in even longer form, but it will pay off eventually. Okay. Let's call this equation 1. And how we do is we write this as a polynomial with matrix coefficients. Okay. So what we mean is the following. We look at the s squared terms. Okay, here we have minus 6 for the s squared, here we have 3 for the s squared, here we have 1 for the s squared, and here we have no s squared term, therefore 0 for s squared. So that makes this matrix times s squared, and that matrix is minus 6, 3, no s squared term anymore. Plus, okay, you do the same thing for s, and you do the same thing for the zeroth order terms. For the s's, you have what? Here we have 2s times minus 6 minus, excuse me, 4s times minus 6 minus 24. Okay, then the rest is 15 over 2, 1/2, 3 over 2. Okay, and for the zeroth order terms, what we have is 2 squared 4 times minus 6 minus 24. You have 2 times 1/2 times 3. That's 3. Here you have 1/2 times 2. That makes 1. And here you have 1 times 1/2. That's 1/2. Divided by ds. So that's our g bar of s. And that completes our step 3. So far, what we have done looks a bit meaningless, but it will gain meaning at the very end once we start recognizing some very elegant patterns that will allow us to obtain the ABCD matrices. Okay, step 4. This is the step where we take our first read to the time domain. In other words, we choose our state. Okay. Define the state x in, okay, so what's the dimension, what's the size of the state in this representation? It's 6, and 6 equals 3 times 2. Okay, what's 3 and what's 2? 3 is, okay, is degree of our common polynomial, d of s, okay, and 2 is the number of inputs. So why do we have 2 inputs? Because our transfer function matrix has 2 columns. Okay. Hence, let's write x as x1, x2 up to x6. But we will adopt a slightly different notation because it's easier to work with that notation. We're going to let x to be x1, x2, x3. Now x is a vector in R6, so its size is 6, but now we have 3 entries. Therefore, these entries themselves must be vectors. And if that's the case, x1 is a vector in R2, x2 is a vector in R2, and so on. So we have 3 vectors, each in R2. So the whole vector is a vector in R6. Okay, x1, x2, x3, each in R2 real plane. And once again, this 2 is number of inputs. Okay, and now we define the states x1, x2, and x3 are sort of state variables, which are vectors, in the following sense. We start with x3. x3 of s is, we're choosing it, its definition, is u of s over the polynomial d of s. Okay, and then x2 of s is x3 of s, so in time domain it's the time derivative of x3, and x1 1 of s is s squared times x3s. Okay, for zero-dimensional case, it means x3 double dot in time domain, or x2 dot Okay, so that's what x1 is. Okay, having chosen the state, now we're ready to begin constructing our ABCD matrices. Okay, so remember that this is our equation. So this was R G bar of S. Okay. Now let's start from this equation and rewrite it as follows: D of S times x3 of S is U of S. Now I'm dropping for the sake of simplicity this S terms here. Okay. So our common polynomial multiplying x3 Laplace transform of x3 equals Laplace transform of input. So let's remember our common polynomial in its open form. Okay. And that yields s cubed x3 plus 9 over 2 s squared x3 plus 6s x3 plus 2x3 equals the input. Okay. Therefore, we can write s cubed x3 equals. So we leave this guy here and throw everything else to the right hand side. And we have minus 9 over 2 s squared x3 minus 6s x3 minus 2 x3 plus u. Okay. Therefore, now s cubed x3 is s times x1. Okay. So this thing we can write as s times x1 equals. Okay. S squared x3 is x1. Okay, so we have minus 9 over 2 x1. S times x3, by definition, it's x2. So we have minus 6 x2, and we have minus 2 x3 plus the input u. Okay. And then we write s times x2. Okay, what's s times x2? S times x2 is s squared x3, and s squared x3 is x1. Okay, so here we have x1. And finally, we have s times x3, and that's by definition x2. Okay. Now here we have the state multiplied by s in Laplace domain. We know that in time domain these will be dots, x1 dot, x2 dot, x3 dot, under the assumption that's the initial conditions are 0. So that means we're very close to our A and B matrices. So let's collect these and rewrite them in matrix form s times x1, x2, x3 equals some matrix times x1, x2, x3 plus some matrix times u. This will be our equation number 2, and that it will give us A and B matrices. Okay. So what are the entries of A and B matrices? For that, all we have to do is look at here. Okay. Now, for the first row, we look at the first equation. We have minus 9 over 2 x1 minus 6 x2 minus 2 x3 plus u. So let's write it down. Minus 9 over 2 minus 6 minus 2. And here we have 1. But the problem with that is the following. Okay, so these are, okay, so this is a vector in R6 Okay? This is also vector in R6, and we're transforming a vector in R6 to another vector in R6. Therefore, this should be a 6 by 6 matrix. But if you fill in the entries by looking at these coefficients, what's going to happen is you obtain a 3 by 3 matrix. Therefore, what you should write down here is this identity matrices. Okay. So we have -9 over 2 identity, -6 identity, -2 identity, and that's the identity matrix of size 2. It's 2 by 2 identity matrix. Likewise, we have Sx2 equals x1. So that means here we have ms2 should be an identity matrix 0, 0. And finally, and this 0 is vector 0. And finally, we have Sx3, which is x2. So that means 0, identity, 0, and 0. Okay, this identity matrix is 2 by 2 identity matrix. Okay, so let's call this equation 2. Now, what we have is y of s equals g of s times u of s, and g of s we have written as g bar of s plus d times u of s. Okay. Then, by using our equation 1, which was a nice expression of g bar of s, our strictly proper part of the transfer function, and what we have is we can write, okay, this g bar of s times u of s as follows: -6,301 times s squared u over d of s. And then we go to the next matrix coefficient, -24, 15 over 2, 1/2, 3 over 2 times su over ds, okay, plus -24, 1, 3, 1/2 u over ds. Okay, finally let me squeeze here d times u, which is 2000 times u. Okay, so this of course equals y. Yes, equals, so this you obtain from 1. Okay, now we have to recognize certain terms here. This is no other than x1, this is no other than x2, and this here is our x3. Okay, x2 is s times x3, and x1 is s squared times x3 by definition. Okay, and let's call this equation 3. So equation 2 and equation 3, when we go to time domain, will directly give us our ABCD matrices. So let's write down the final answer. Okay, now let's take the inverse Laplace transform of equation 2 under 0 initial condition assumption, so that this will immediately give us the time derivatives. So what we have is x dot equals this 6 by 6 matrix times x plus this 6 by 2 matrix times our two-dimensional input u. Okay, so we have blocks for our 6 by 6 matrix, and we have also blocks for our 6 by 2 B matrix. Okay, this is our A matrix, its size is 6 by 6. This is our B matrix, its size is 6 by 2. Okay. This entry is minus 9 over 2 times identity matrix, and by identity matrix we read it 2 by 2 identity matrix. So that means we have minus 9 health, minus 9 health, 0, 0. This is minus 6 times identity matrix. So that means minus 6, 0, 0, minus 6. Here we have minus 2, 0, 0, minus 2, and so on. 1, 0, 0, 1, 1, 0, 0, 1, and everything else is 0. Okay, 36 entries. Now for B we have 0, 0, 1 identity, and the remaining entries are 0. And how about C and D matrices? For that, we look at our last equation, equation 3, and write y equals C times x plus D times U. What's x? What's C matrix? Again, let's write it as 1. So we have minus 6, 3, 0, 1 for x1. We have minus 24, 15 over 2, 1 half, and 3 over 2. And finally, this constitutes this last block, which is minus 24, 3, 1, 1 half x. As for D, it was obvious from the very start, and it's 2, 0, 0. This is our C matrix, and clearly its size 2 by 6. And this is our D matrix, size 2 by 2. Okay. Now, since each step, I believe, was clear, so it's more or less straightforward how to generalize this controllable covariant representation algorithm for an arbitrary transfer function matrix. Okay. Now, since for a given transfer function, the ABCD representations are not necessarily, well, the ABC representation is not unique. That fact motivates the following definition of equivalence between representations. So first, let us put our observation down. 2 different particles A, B, C, D. First one and the second one, let's call them A bar, B bar, C bar, and D bar. Okay. May yield the same transfer function. Okay. If they do, in other words, if C times Si minus A inverse B plus D, this is the transfer function given by the first set, equals C times Si minus A inverse B plus D this time with bars everywhere, which is a transfer function corresponding to the second set. Then those 2 representations, or my slight abuse of terminology, those 2 systems, namely, the first system x dot equals ax plus bu, y equals cx plus bu. And second system, let's choose another state notation for it. Let's call z dot equals plus b bar u and y equals b bar u. Okay. Are set to be zero state equal So that means, or interpretation of that is, since they have the same transfer function, means that you, for both of those systems, set the initial conditions to 0, x0 equals 0, z0 equals 0. And then excite both systems with the same input, and at the output, you should see the same response. Okay? No matter what the input is. So such pairs are called zero-state equivalent pairs. Okay, so let's write them down. If two systems are zero-state equivalent, ZSE, then under zero initial conditions, they give the same response. At their outputs. Then excited by the same inputs. Quite a intuitive definition. Now let's also talk about, because it's important a bit, about a stronger version of equivalence between a given pair of systems. And it's called algebraic equivalence. Okay. Algebraic equivalence. Okay, so suppose that we start with the following given system. Given the state space representation, x equals ax plus bu and y equals cx plus bu. Let's call this system 1 or representation 1. Now let T be an n by n non-singular matrix. Where n is the order of the system, therefore x is in Rn, or A is an n by n matrix, and so on. Now, for this system and for this transformation matrix T, define the new variable. We're going to call it new state, okay, Z, which is T times x. Okay. Now, since T is non-singular, it means it has an inverse. Hence, if you know Z, you can figure out what x is. Inverse x equals T inverse times Z. Okay. Now, the question is, how about the dynamics of the Z system? Okay. So, if you choose for the same system state as Z. So what happens to the ABCD matrices? So let's figure that out. It's quite straightforward. Then we can write Z dot equals, T is a constant matrix, therefore Z dot equals T times X dot. Okay? And X dot is here, let's write it down. So that equals T times AX plus BU. Okay? And that equals TA times X, but we want everything in terms of Z, and X is T inverse Z. Hence here we have T inverse Z plus TBU. So that's our Z dot. That's the right hand side for Z dot. What else? Also, Y equals CX plus DU. X is T inverse Z, so we can write CT inverse Z plus DU. So that's the expression for the output in terms of the new state and the input. Now, what we're going to do is we're going to recognize the new ABCD matrices of the Z system. Now, let the matrices A, B, C, and D tilde be defined as, okay, this is A tilde, TA, T inverse. This is B tilde, TB. This is C tilde, and B tilde is D itself. Okay. Suppose we adopt this notation. Let's call this set of transformations from ABCD to tilde versions as star. Then Z dot equals A tilde Z plus B tilde U, and Y equals C tilde Z plus B tilde U is a new system whose state is Z. It's a new system. And how about the property, or how about the relation of this new system to the original representation? It's the following, which is not difficult to believe. This new system, okay, system 2 over there, has the property that if its initial condition is chosen according to the rule here, that is Z0 equals T times the initial condition for the original system, then for the same input, the outputs of system 1 and system 2 will be identical. Now this motivates us to define the following concept, which is much stronger than the earlier defined zero state equivalence. are definition. Two LTI systems which we numbered earlier as 1 and 2. 2 is already on the board, 1 I just erased, are said to be algebraically equivalent if there exists a transformation matrix, sometimes called a change of coordinates matrix. There exists a non-singular matrix such that set of equations T such that the set of equations that we label by star, okay, this set holds. Okay. So through that change of coordinates matrix, you can go from one set of parameters to the other set in the following fashion. And that Z equals Tx is called similarity transformation. Sometimes. Okay. And it's a very useful analysis tool. Given some system in original coordinates, sometimes certain things are not easy to see. So what you do is, using intuition, sometimes, and sometimes by other means, you pick a clever transformation matrix so that once the system is passed through that transformation, in the new coordinates, many things become easier to see, like controllability, stability, observability, and many other behaviors. Okay. Therefore, it's a very widely, frequently used tool for analysis, that is, obtaining a new system through change of coordinates. Let's end this lecture with the following easy exercise. Show that algebraic equivalence is a stronger condition than zero-state equivalence, meaning that if algebraic equivalence holds between two systems, then those two systems are automatically zero-state equivalent. However, the reverse is not true. Zero-state equivalent does not imply algebraic equivalence.